So it appears from your responses that only 40% of the students are attentive. We had quite a big discussion on what is a reversible adiabatic process in the last lecture. And a very simple, straightforward question has been asked to you in the poll, wherein I am asking you what would happen to the entropy if the process is reversible and adiabatic. So adiabatic process, adiabatic reversible process. When you talk about, you know that there is no heat exchange in such a process. Okay, and together with that fact that the process is also reversible, you must understand that there is no chance of the entropy changing, right? However, looking at your responses, it appears to me that not all of you are appreciating this fact. So the plan of today's lecture is to continue with our discussion on look at this. What we are doing in the last couple of lectures is we are basically estimating or we are rather considering the systems involving ideal gases, and we are applying the first law of thermodynamics to it, both the open systems as well as closed systems. We are eager to calculate what is the heat transfer, what is the work transfer, and what is the entropy change. So these three important terms, that is the heat transfer, work transfer, and entropy change, they are asked many times in the exam, especially in the context of ideal gases. Okay, so you must be comfortable with this sort of calculations. Okay, and in the real life also you would be needing those, because I told you that ideal gases, when you are talking about ideal gases, such a assumption of a working fluid being an ideal gas is made when you do a preliminary analysis of systems like internal combustion engines or gas turbines, okay, or even compressors for that matter. So all the many practical systems, okay, like compressors, gas turbines, okay, internal combustion engines, they can be assumed to have the working fluid as ideal gas. So we need to be comfortable with such calculations. Okay, we must know what exactly is happening. We need to figure out whether the system is a closed system, open system, and then apply the appropriate property relations for that. Okay, so let me close the poll now, and let me before there are only 84% of the students have still voted. I want you, all of you, to vote for this question. Okay, so before I begin my presentation, in the plan is today to solve one numerical on a reversible adiabatic process, closed system. Okay, and then if time permits, we'll take another process. So that is the plan of today's lecture. Okay, so let me share my whiteboard. I have not yet closed the poll. Those who have not yet voted, they need to vote for the poll question. Okay, so let me close the poll and let me tell you the correct answer. So as you see on the screen of yours, what we see is that 43% of the students have answered the poll question correctly. Okay, and the remaining 57% of the students have answered it wrong. Okay, so why they have given it as a positive value or negative value? The only reason is that they have not understood anything, they were not attentive, and that is the reason why they are giving the answer as positive, negative, and whatnot. Okay. So the correct answer to this question is when the process is reversible as well as adiabatic, reversible and adiabatic process, then there is no chance of change of entropy. The entropy would remain constant, and such a process is called as an isentropic process. Okay, this isentropic process you would encounter in many practical cases when you analyze the gas turbine, steam turbine, all those things, where you would make an assumption that the entropy would remain constant. Then, okay, so it's a very important process to be kept in mind that when the process is reversible and adiabatic, it is essentially an constant entropy process, isentropic process. Okay, and now let me close this sharing of the poll and show you the whiteboard. So I'm closing the poll, and now I would be showing you my whiteboard. Let me show you the whiteboard. Just a minute, it is loading it, and I haven't erased anything or whatever we had discussed yesterday. So once the whiteboard is seen to you, you would start noticing this display. Okay, it is taking time. Yes, now it is now seen. So you see that just revise this a bit because I feel that most around 60% of the class is still not able to appreciate what we had discussed. Okay, so on the whiteboard, what you see is I have shown. I'll just rub few the things. I'm concentrating my attention only on closed system now. Okay, for I'll be having the open system diagram here. I'm erasing the open system. Okay, so let me erase the open system. Okay. Some students at least must have tried the proof for the derivation for the work transfer of open system. At least 10% of your class students who are much more interested. I hope that they have tried the other derivation. I had asked you to derive in the yesterday's class an expression for the work transfer in a steady flow system. Okay. Uh, so for the non-flow, you know that and the work transfer is given by integral of PdV, and for the flow is non-flow process, that is a closed system, and if it is a flow process, then it is integral of PdP. Okay, so if you do the derivation for the integral of PdV, then you will get an expression like mr T1 minus T2 upon gamma minus 1. Okay, so you can derive this expression from this using this relation. Okay, so we had discussed this derivation in the last lecture. So those who were not attentive, they can refer to the notebooks of students. Okay, and maybe I will be sharing the link of this video also later. So this expression is very important. Okay, for calculating the work transfer if the process is a reversible adiabatic process exhibited by the closed system. Okay, so by closed system I mean arrangement like this. For example, a piston cylinder arrangement without walls and insulated one because the heat transfer is zero and the piston is moving. Okay, the piston is moving, so either it is moving away from the top dead center, then it is a case of expansion, and if it is moving towards the top dead center, it's a case of compression. In either case, what you would find is that the entropy would remain constant. Okay, and it would be a vertical line on the temperature entropy diagram. Okay, so this would be more clear to you as you solve a numerical. So take down one numerical now. A gas which is at 1 bar and 27 degrees centigrade. We write down this numerical. A gas which is at 1 bar and 27 degrees centigrade. 27 degrees centigrade. I am also erasing this entire thing, and I will also try to write it on the board, but you can listen to my voice and you can take down the question. Okay, so what are we doing? We are solving a numerical, okay, today, involving the process which we had discussed in the yesterday's class. That is, we are talking about a numerical which is a closed system numerical, a numerical which is involving ideal gas, or the gas which behaves as an ideally, okay, and a numerical which in the gas is performing a process which is not only reversible but also adiabatic. Okay, so we are solving a numerical to demonstrate so that you appreciate this better. So this is a university numerical. It was asked in some exam for 6 marks. So a gas is given which is at a temperature of 1 bar, pressure of 1 bar and a temperature of 27 degrees centigrade. Okay, this is compressed in an engine. This is compressed. And how is it compressed? It is compressed reversibly and adiabatically. The gas which is at 1 bar 27 degrees centigrade is compressed reversibly and adiabatically in an engine. Okay, in a reciprocating engine, that is a piston cylinder arrangement, you can say piston cylinder arrangement, to a final pressure of 25 bar. Final pressure of 25 bar. Okay. What you need to find out is the work transfer during compression. The work transfer during compression and entropy change. Okay. Entropy change. You can also find out, for example, the enthalpy difference, enthalpy change also you can find. Okay, so this is a question. The given data is the specific heat of gas at constant pressure is 1.005 kilojoules per kg Kelvin, 1.005 kilojoules per kg Kelvin, and the CV value you can take it as 0.717 kilojoules per kg Kelvin. Okay, so I want you to calculate the work transfer. I want you to calculate the the entropy change and the enthalpy change. I'll be representing this process on a pressure volume diagram. Okay, this process is compression. So obviously, the arrow as shown is towards the vertical. It's a curve, and this curve, because it is a reversible adiabatic process, curve would obey the law P into V raised to gamma is equal to constant. Okay, because it is a reversible adiabatic, process. Okay, so P into V raised to gamma is equal to constant. Let us say the initial state is 1 and the final state is 2. Okay, so it means that using our notations, P1 is 1 bar and T1 is 27 degrees centigrade Okay, 27 plus 273, that is 300 Kelvin. Okay, it's always a good idea to convert the temperature into Kelvin, because all your gas relations would require capital T and not small t while solving the numerical. Okay. First, what you could do is that you could step by step we'll do. We want the final. You know the final pressure is P2, that is 25 bar. So I want you to calculate the temperature T2. Okay, I want you to calculate the temperature T2. So tell me the temperature T2. How will you calculate the temperature T2? So what we do is that when your process is reversible and adiabatic, then we use the relation T2 by T1. T2 by T1 is equal to P2 by P1. For an adiabatic process, we use this relation gamma minus 1 by gamma. And how come this relation comes? So if you are interested, you can prove this relation. How to prove this? You need to solve this two simultaneous equations. P1 V1 by T1 is equal to P2 V2 by T2. You can solve this to this is one simultaneous equation, and the other simultaneous equation is P1 V1 raised to gamma is equal to P2 V2 raised to gamma. So if you solve these two expressions, and if you eliminate the volume terms, what we'll get is the expression in terms of temperature and pressure. That is, let me use another pen. So the expression which is enclosed in a blue box, that is T2 by T1 is equal to P2 by P1 whole raised to gamma minus 1 by gamma. This expression is the expression we can derive, and this expression is applicable if the process is a diabatic process. Okay, a diabatic process with for the gas whose adiabatic index is 1.4, gamma is 1.4. So solve this and tell the value of temperature T2. Solve this and tell me the temperature T2. While you post your answers, write your names. Okay. So solve this and tell me the temperature T2. And why are we finding temperature T2? Because we are interested in finding the work transfer. Okay, work transfer. So any answers? So how will you solve this? T2 is equal to T2 will be equal to T1 into P2 by P1 raised to gamma minus 1 upon gamma. Gamma is 1.4 and T1 is 300 Kelvin. P2 is 25 bar and P1 is 1 bar. Okay, so you solve this and you get some answer in Kelvin. Tell me that answer. Tell me this answer, Vedant. Okay, Neha has answered it correctly. Neha has got this answer. Thank you, Neha. So the answer which Neha has got and which is correct is 752.54 Kelvin. 752.54 Kelvin. Okay. So now we have got the value of temperature T2. It means that when this gas is compressed, so gas was initially at a temperature of 27 degrees centigrade, the pressure was 1 bar. Okay, now because of compression, the temperature of the gas is increased and now it has reached 752 Kelvin. Okay, it means let me write the answer in Kelvin. Okay, so the initially the temperature was 300 Kelvin, and now it has increased to 752 Kelvin. And why has it increased? It has increased in spite of the fact that there is no heat transfer. Whether there is heat transfer? No. There is no heat transfer. Why is there no heat transfer? Because the process is adiabatic. Okay. So adiabatic process, no heat transfer, and yet you find that the temperature of the gas is increased. So this is because your gas is being compressed. Gas is being compressed. And why is the gas being compressed? The gas is being compressed because of work transfer. So now you calculate the work transfer. The gas is being compressed because of work transfer. So calculate the work transfer now. We had already derived the expression for work transfer. So let me write down that expression for work transfer which we had derived when the process is a reversible adiabatic, when we are dealing with the closed system. Okay, so let me write down that expression. Okay. So I'm writing this expression for work transfer now. Okay, I'll be using some other pen here. So the expression for work transfer is as follows. It is equal to, you know that it is integral of PV, and we can derive it in terms of temperatures also, and I talked about the derivation. So it becomes MR T1 minus T2 upon gamma minus 1. Okay, gamma minus 1. Another expression you also know, if you remember that, the other expression which I derived is in terms of P1 V1 minus P2 V2 upon gamma minus 1. So this is one expression and this is another expression. So I will be using this expression now. So mass is per kg will find. So every kg the work transfer, specific work transfer, it means R you know is 0.288 kilojoules per kg Kelvin. Okay, the temperature is T1. So the temperature is 300 initially, and finally the temperature shoots up to 752.54. Your value gamma is 1.4. So tell me the value of the work transfer. Tell me the value of work transfer kilojoules in kilojoules. Calculate and tell me the answer of work transfer. Okay, Vedant has got some answer, and whether it is positive or negative, Vedant, whether the value, yeah, it is negative. Correct. Correct. Thank you, Vedant. Anybody else who has got the answer? So Vedant, thank you. The answer is minus 325 approximately. Okay, so minus 325.8 kilojoules. Minus 325.8 kilojoules. Now, what is the meaning of negative? Why it is negative? Sushant, thank you. Why is it negative? Sushant, why is it negative? What is the meaning of the negative sign? Okay, Gargi is correct. The work is done on the system. Okay, we are supplying the work. The work is done on the system, so it is negative, right? So mind well, yeah, correct, Vedant. We have got now the work transfer. What else is asked now? To calculate now the entropy change and enthalpy change. Calculate the entropy change and enthalpy change. How do you get R? I had calculated as Cp minus Cv. Okay, or you can also remember the value. Cp minus Cv is coming as 0.288. Okay, because Cp is given and Cv is given, so I had subtracted Cv from Cp, and that gives me R. So R is Cp minus Cv, which is 0.288. Okay. How to find the change in enthalpy? change in enthalpy from the definition of specific heat is mCp delta T. mCp delta T. So let me erase this and let me write down the expression for change in enthalpy. Talking about change in enthalpy. So change in enthalpy delta H is mCp delta T. Okay, so it is 1 into specific heat is 1.005 and delta T is, it is 300 minus 752. 300 minus 752. So that gives me the value of delta H. So change in enthalpy, Vedant has got the answer correct. It is negative. Okay, so enthalpy would decrease. Enthalpy would decrease, right? Sorry, T2 minus T1, H2 minus H1. I'm sorry, it is not. It won't be negative. H2 minus H1, so it would be T2 minus T1. T2 minus T1, and obviously the enthalpy would increase. And why would the enthalpy increase? Because you are transferring work to it. So when you are transferring work to the gas, the enthalpy of the gas would increase, right? So it will be a positive value, not negative. So just make a correction here. The temperature is 752 finally. So 752 minus 300. 752 minus 300. So that gives us the answer as 454. Just see whether I am correct. It is some 454. Is it 454 kilojoules approximately? This is the answer, whether you are getting it as 454. Okay. Yeah, right. So Vedant is right. It is 454 approximately kilojoules. This is the change in enthalpy. Now find the change in entropy. Find the change in entropy. Change in enthalpy is 454 approximately, and now find the change in entropy. So how do you find the change in enthalpy? mCp delta T. mCp delta T is the change in enthalpy. How did you find the work transfer? P1 V1 mR T1 minus T2 upon gamma minus 1. Gamma minus 1. And how did we derive this expression? We derived this expression by solving the integral PdV. Integral of PdV. And why we had used the expression of integral PdV? We had used the expression of integral PdV because the system is a closed system. If it was an open system, we would have used another expression for work transfer. So when it is a closed system, the area under the diagram is basically the work transfer. Okay, so the area under the PV diagram is the work transfer. So because correct, Vedant, you are right. So because the process is adiabatic process means there is no heat transfer, and because the process is reversible, so there is no question of change of entropy. So the entropy change would be zero. Entropy would remain constant. Okay, so the answer is entropy change delta S is equal to 0 because the process is adiabatic and reversible. Okay, so I hope it is clear to you. So the solution of this problem is 1. Work transfer is minus 325 kilojoules. The enthalpy change is around 454 kilojoules, and the entropy change is 0. Entropy change is 0. So these are the answers. I hope it is clear to you. Okay, so what kind of system did we consider? We had considered a closed system. And what was the process the gas was undergoing? The process was a reversible adiabatic process. Okay. So let me erase this problem and go to the next concept. Before I go to the next concept, let me ask you one question. I'm asking one question here. If the process is adiabatic, if the process is adiabatic and irreversible, what would be the entropy change? What would be the entropy change? Whether the entropy change would be the option A. Option A is, let us say, sorry, why I'm writing it as option. Let me just erase this. Option A is it is 0. Option B is it is positive. Option C is it is negative. So tell me this answer. Okay, the question is clear to you. I want you to answer this. If the process is adiabatic and irreversible, what would be the entropy change? Adiabatic and irreversible, what would be the entropy change? Cyrus has got some answer. Garge is saying it is 0. Think over it, okay? Tejas is saying it would be positive. Otherwise saying it is positive. Vedant is saying it is 0. So Gargi and Vedant are sure that they are 0 because the process is adiabatic. Ritesh is saying it is positive. It is adiabatic, so heat transfer is 0. So Ganesh Jadhav is saying it is 0. Sushant Kannada is saying it is 0. Neha is saying it is positive. Ritesh is saying it is positive. Ganesh says it is 0. So you need to, okay, Anish is saying it is 0. Mohan says 0. So let us now discuss this, and this should be very clear to you. If you had remembered our discussion, Garge is saying 0. Nikhil is saying 0. See, remember our expression for entropy change for a process, okay? For a process, for any process, the change in entropy is greater than equal to del Q by T. Del Q by T. Okay. Or delta S, if I want to write it not in the differential form, delta S is equal to, sorry, delta S would be greater than equal to integral of del Q by T, integral performed along a reversible path. Okay, performed along a reversible path from 1 to 2. From 1 to 2. That means that S2 minus S1 would be greater than equal to delta S. So if I want to replace this inequality by, if I want to replace this inequality by equality sign, then it means it was like this. You don't understand mathematics. So delta S would be equal to integral of del Q by T performed along a reversible path if the process plus entropy generation, which has to be always positive, because if this term has to be greater, then this delta S, this S generated, entropy generated, always has to be greater than 0. Then and then this inequality can be replaced by equality. Okay, so this term is called as, this is entropy change because of the heat transfer. So it's called as entropy transfer. As the entropy change, because along with the heat flows the entropy. Along with the heat flows the entropy. Now look at this way, that the entropy, if there is an entropy transfer, suppose there is a system. Okay, there is a system, and let us say you are transferring certain heat. to the system, and this heat transfer is irreversible. Heat transfer is irreversible. So what would happen to the entropy of the system? The entropy of the system would increase. Why would the entropy of the system increase? The entropy of the system would increase. The entropy change would be positive because the heat is being transferred to the system. Heat is being transferred to the system. One thing, and second thing, because of irreversibility, Okay, so these are the two ways the entropy can change. One is because of heat transfer and because of the irreversibility. Right. Now consider this is case one. Let's say case one. Okay. Now case two. Let me draw this again. Case two. Let us say that there is a system. Okay, and this system, the heat transfer. So it is an adiabatic system. So it is an isolated system. Okay, adiabatic system, and this system undergoes certain reversible process. This is a reverse. So, or first, let me say that it undergoes an irreversible process. Okay. So in such a case two, the heat transfer is zero. So the delta S entropy change. So in this case, the entropy change because of heat transfer is zero. Because of heat transfer is, because there is no heat transfer, so the entropy will not flow in. However, because the process is irreversible, there would be certain entropy generation. So in the case two, what would happen? What would happen to the entropy? The entropy change would be positive. Okay, so the entropy change would be greater than zero. Why it would be greater than zero? Because it won't be zero. In case one, the entropy change would be zero. Case one, the entropy change would be positive. Okay. Case two, also the entropy change would be positive. Now consider case three. Let me consider case three. Case three. We are talking about certain system here. There is a system. Okay, there is a system. There is no heat transfer, and the system is undergoing a reversible process. So the system is adiabatic because there is no heat transfer, and the process is reversible. So such a case, so the system is undergoing a reversible process and there is no heat transfer. In such a case, delta S has to be zero. That is, entropy is constant. So it is an isentropic. So case 3 is an isentropic process. Because in this case there is no heat transfer and hence there is no entropy transfer. There is no heat transfer, there is no entropy transfer. Entropy transfer is zero, and because there is no irreversibility, the process is reversible, so the entropy generation is also zero. So entropy generation is zero, this is zero, and entropy generation is zero, entropy transfer is zero, hence delta S is equal to constant. Okay, in case 2, entropy transfer is zero because heat transfer is zero. However, entropy generation is positive. Why? Because of irreversibility. Now consider case 4. Where a system is rejecting the heat. system is rejecting the heat, and this heat transfer is reversible. Heat transfer is reversible. The system is rejecting the heat, and this heat transfer is reversible. So what would happen to the entropy now? What would be delta S? Case 4, tell me what would be the delta S value. Case 4, system is rejecting the heat, and the system, and it is reversible. So in this case, the entropy of the system would decrease, right? Now let us consider another case. Are you getting the point? Yeah, correct. Gargi is correct now. So it means that if you think of the problem which I had given, the process is adiabatic and the process is irreversible. So it is which case? Process is adiabatic, and so it is a case 2. It is a case 2. If the process is adiabatic, so the entropy transfer would be 0. Entropy transfer would be 0. However, because of irreversibility, the entropy change would be positive. So the correct answer to the question is, because this question falls in the case 2. Because this question falls in the case 2, so the correct answer is the entropy change will be positive in spite of the fact that the process is adiabatic. So note that when the process is adiabatic and irreversible, then the entropy change is not 0. Then the entropy change is positive. If the process is adiabatic and reversible, then the entropy change is 0. I hope it is clear to you. Okay, I'll just, in short, I will write down this again, and then we will move to the next topic. So note that, I'll just highlight this again, that if the process is reversible and adiabatic, then the entropy change is 0. Then the process is constant entropy process. Then it is a constant entropy process. If the process is irreversible and adiabatic, then delta S is greater than 0. Okay, and this is because of entropy generation. Okay, or in other words, it is because of irreversibility. What is case 1? What was the case 1? I forgot about the case 1. Okay, what was the case 1? I guess we were talking about system, and there is a heat transfer and there is a irreversible heat transfer. Okay, so what is our expression for delta S? Delta S is entropy transfer, so change in entropy because of heat transfer, and entropy generation. This is for irreversible process expression. Okay, this is the irreversible process expression. Okay. Now because the process is irreversible, this is positive, and because the entropy would flow into the system, this would also be positive. So the entropy change has to be positive. I hope it is clear to you, Gargi. Okay, I hope it is clear to you. Right? So because the heat is flowing into the system, I don't want to complicate the matters for you. You can think over this. Consider this. Okay, and this is left as homework to you. Where the system is rejecting certain heat Q, and this heat rejection is irreversible. Okay, heat rejection is irreversible. Then just to confuse you a lot, okay, those who are interested in this confusion, okay, so in that case, what would happen to the entropy? Okay, whether it would be 0 entropy change, whether it would be positive or whether it would be negative. I don't want to answer this question now. It is left as a homework. The system is rejecting the heat irreversibly. In that case, what would happen to the entropy of the system, whether it would be 0, whether it would be positive, whether it would be negative, or whether the answer is it depends. Okay, these are the 4 options. Okay, so I won't be discussing the answer now for this. So let me move on to the next case, that is of isothermal heat transfer or a polytropic heat transfer. I'll take first a polytropic heat transfer case. Let me erase this and let us discuss another ideal process, which is actually very much relevant because you know that mostly we talk about the processes being polytropic processes. So when you are saying polytropic process, it means that it follows the law P into V raised to n is equal to constant, and this n is known as the polytropic index. Polytropic index. We'll discuss the closed system case. Closed system case, and you will derive the expression for work transfer. We'll derive the expression for work transfer. Derive the expression for work transfer. So how will you derive the expression for work transfer? So the work transfer, because it is a non-flow process, closed system process, is given by integral of P dV from 1 to 2. Okay, so how do we do that? So substitute the value of P as C upon V raised to n in this equation and solve. So try doing this. Try doing this derivation. So what will be left with is like this. W is equal to integral of C into V raised to minus n dV from 1 to 2. C being constant, I can take it outside the integral. 1 to 2 V raised to minus n dV, which is equal to C into V raised to minus n plus 1 upon V raised to minus n plus 1. Okay. Plus 1 from 1 to 2. Sorry. N plus 1 from 1 to 2. Okay, and you need to just this. I will do the method of solving this. What you need to do is that 1 upon minus n plus 1 C upon this V2 minus n plus 1 minus V1 minus n plus 1. Okay, you solve this. Use the same trick as we had used for adiabatic process while multiplying C inside here. Okay, so C, put this C as, while multiplying this with V2, put the C as P2 V2 raised to n, and when you multiply the C with V1, put that C as P1 V1 raised to n. Okay, so substituting this value of C, you will get a similar expression. That is, you will get an expression of the form P1 V1 minus P2 V2 upon n minus 1, or which is same as, because PV is equal to MRT, PV is equal to MRT, so this will be MR T1 minus MR T2 upon n minus 1. So look at the expression and look and compare it this expression with the expression which we had derived for a reversible adiabatic process. So instead of gamma, you will find that in this expression you have a polytropic index. Yeah, you have a polytropic index. Yeah. Okay. Now let us. I hope this is clear to you. This expression for work transfer. So let me erase this. I'm clearing this canvas. Okay. Similarly, you can find the expression for work transfer when the process is. Similarly, you can find the expression for work transfer when the process is isothermal process. Suppose the process is reversible isothermal. Isothermal means temperature is constant. So PV is equal to MRT becomes PV is equal to constant. Boyle's law. Okay. So PV is equal to constant, and if it is a closed system, the work transfer non-flow is integral of PdV, that is the area under the curve, PV process line, area under the process line, PdV, and hence this would be, because PV is equal to constant, so P is equal to C upon V. P is equal to C upon V. So to put it over here, so this is a matter of all these derivations. You will find that they are a bit boring, but there is no alternative, but you need to practice a lot. In the exams, you might be asked such kind of derivations. Okay, derive the expressions for work transfer, heat transfer, if it is a closed system, open system like this. Okay, so this is solved again. It would be what? It would be C log to the base C V from, suppose we are integrating from 1 to 2. This is 1 to 2, 1 to 2. So this would be 1 to 2. So this is C log to the base C V2 by V1, and C is nothing but P1 V1 log to the base C V2 by V1. Okay, so such kind of derivations you must do. All right. So what is this process? This is the expression for work transfer. If I want to write it in terms of MR T1, P1 V1 is equal to MR T1 log to the base C V2 by V1. Okay, how would the isothermal process look on the temperature entropy diagram? How would the isothermal process appear on the temperature entropy diagram? Any answers? How would the isothermal process appear on the temperature entropy diagram? On a temperature entropy diagram, the isothermal process would appear as a horizontal line. If the heat is added, it would be like this. This is the heat added, entropy would increase isothermally. Okay. If heat is rejected, the temperature entropy diagram would look like this. This is the heat rejected. Okay, heat rejected isothermally, and this area under this is heat transfer. This is the heat transfer. Okay, this area under this is the heat supplied. Okay, so this you must appreciate, right? This you must appreciate. What would be the change in what would be the heat transfer for closed system? This is the work transfer. No? How to calculate the heat transfer for a closed system? So closed system heat transfer, you would apply the first law of thermodynamics, mathematical statement for a process closed system. So Q1 to 2 is equal to delta U plus W1 to 2. Now change in internal energy when the process is isothermal. So from the definition of internal energy, delta U is equal to CV delta T. And because the temperature is constant, the change in internal energy is 0. So this becomes 0 plus W1 to 2. It means that when the process is isothermal, the expressions for the work transfer and heat transfers, they are same. When the process is isothermal, the expressions for work transfer and heat transfer in case of closed system, they are same. They are same. Okay, I hope it is clear to you. So the work transfer and heat transfer can be calculated if the process is a closed system. If the system is a closed system undergoing a isothermal process, so this is the expression you must use. This is the expression you must use. Okay, hope it is clear to you. What would be the expression for entropy change? What would be the expression for entropy change in this case? If it is a isothermal process. So for entropy change, integral of del Q by T, which is equal to, which is what? Integral of, because del Q is del W and del W is PdV in case of thermal process. So I can put this value as PdV upon T. Okay, and I know that PV equal to MRT. So this can be rewritten as P by T is equal to MR by V. So integral of MR dV by V, which is nothing but MR log to the base E. This might sound to you as a calculus lecture, okay, but I am helpless, right? Such kind of derivations are a bit boring, but you need to just go on doing those derivations, okay, to get the relevant expressions. So conceptually speaking, we must understand that when there is a heat transfer isothermally, the entropy would increase. If there is a heat rejection isothermally, the entropy would decrease. Okay, and that is what happens in the Carnot engine. In the Carnot engine, you know that there is a reversible isothermal heat transfer, and the entropy of the working fluid increases there during the heat transfer. And when the heat is being rejected by the Carnot engine, it is rejected at reversibly and isothermally, that is reversibly and at constant temperature. And during the heat rejection, there is a decrease in the entropy. Okay, so this process we had already considered when we talked about the Carnot engine. Which process? I mean to say the process which is reversible and isothermal. Okay. What if the now let me just erase this. I hope it is clear to you. Whether this is clear to you, all of you, this derivation? Okay, Gargi has understood this derivation. Anybody else who has understood this? So it's a matter of calculus. If you are comfortable with integration sort of things, then I don't feel it is very difficult for you to appreciate. For such kind of derivations, you must know only few elementary things, like you must know what is a reversible isothermal process, or what is a reversible isentropic process, or what is a reversible adiabatic process, what are the appropriate gas laws for that, and accordingly derive the things. Okay. So if it is clear, this derivation, I would ask you to derive a similar expression for a reversible isothermal process, but in this case the system is an open system. Okay, assume it to be a steady flow system. So try doing this and tell me the answer. Derive the expression for work transfer. Okay, the question is as follows. The question is as follows. Derive the expression for work transfer during isothermal process undergone by a steady flow system. Steady flow system, you know, is a special case of open system. So in other words, you need to calculate the flow work. So how will you calculate that? Now you need to use the expression minus BTP. Okay. The meaning of expression minus BTP is you are basically finding the area behind this. So minus BTP means you are finding the area behind the curve. This is the integral of VDP. Okay. So again, what we'll do is that we know PV is equal to constant because the process is isothermal. It will follow this law. So V is equal to C upon P. So this becomes, let us say, from 1 to 2 you are integrating. Okay. So integration from 1 to 2 minus dP by P into C. So C I will take outside the bracket. So this becomes C minus C into log to the base Cp 1 to 2, which is nothing but minus C log to the base C P2 by P1, which is nothing but minus P1 V1 log to the base C P2 by P1, which is the same thing as minus MR T1 log to the base C P2 by P1. And if you don't like negative sign, then I can remove the negative sign and write this as plus MRT1 now log to the base C. Instead of P2 by P1 now, it becomes P1 by P2 because I removed the negative sign. Okay. Or in terms of P1 V1, again, if it is positive, P1 V1 log to the base C, P1 by P2, not P2 by P2. Okay. So these are the many terms, expressions for work transfer. If there's a, this is a isothermal process undergone by a steady flow system. to you? Whether derivation is clear to you? Or you want me to repeat whether this derivation is clear? I hope it is clear to you all. Please say yes if it is clear to you. So assuming that it is clear, okay, I'll give a numerical to you to solve. Okay. So the question is as follows. So let us say there is a gas in a closed system. Point 0.014 cubic meter of gas at a pressure of 2070 kilonewtons per meter square expands to a pressure of 207 kilonewton per meter square according to the law P into V raised to 1.35 is equal to constant. Determine the work transfer. Solve. Solve and tell me the answer. So this is an expansion process. Okay. So find the work transfer. What is given is P1 is given 2070, V1 is given P2 is given Tell me the value of V2 first. What is V2? Tell me the value of V2 first. What is the value of V2? How will you get the value of V2? You'll get the value of V2 as P1 V1 raised to 1.35 is equal to P2 V2 raised to 1.35. So this will give you the value of V2. So tell me this value. What is the value of V2? Vedant, Neha, anybody? Atharva, Sairaj, Gargi, Tejas, Ritesh, Sushant, anybody? Tell me the value of V2. So without waiting for your answers, let me write down the value of V2. That value becomes 0.077 meter cube. Okay, and the work transfer, because it is a polynomial process, we have derived this expression is P1 V1 minus P2 V2 upon n minus 1. N minus 1. So this is P1 is 2070 into 0.014 minus 207 into 0.077 upon 1.35 minus 1. So this will give us the value which is around 37 kilojoules. Okay. So make sure that you are comfortable with this kind of problems. Okay, these are not very difficult problems, but you might require to apply your mind as to what kind of process it is and what kind of expression would suit this process. Okay, we can always, if you forget the formula, you can always derive this formula from the first principles. Okay, so that is the beauty of this kind of numericals. You can always, no need of memorizing the formulas, you can always derive them in case you forget those. Okay, so I hope it is clear to you, these concepts. In the next lecture, I would do some derivations which are called as the property relations, and then we would move on to the next topic. Okay, so thanks for being online. I'm ending this webinar. Thank you very much.